promising or surprising, and then suddenly it all gets clear. Or a good piece of music has this sort of funny journey with then the inevitable denouement that feels perfect. So right now it looks bad. But then the idea is, well, maybe 4 wasn't a good choice. What if we made 8 of those and put them together? Now the shape is still not, it looks like maybe a weird caterpillar or something, but it's starting to get a little better. Where I'm going with this argument is that I'm going to show that infinity can help you. Normally people think infinity is mind-boggling and scary. But in math, especially in calculus, infinity is what makes the whole thing work. Infinity is awesomely powerful. And by harnessing infinity, domesticating it, you can do phenomenal things that you can't do with any finite thinking. So this is an introduction to the power of infinity. That is, instead of taking 4, I'm going to take 8 of these. And I put them together like this. And it's starting to look like a little bit of a simpler shape, but still not so good. But it still has that same property. Half the circumference is down here, and half is there, or sorry, and half is on the top. And that thing is still the radius. Notice that it's, if I compare it to the previous one, you see how slopey this is? Compare that slope to the next slope. It's starting to stand up a little straighter. So let me go to 16 and watch the trend. You see now it's starting to stand up quite a bit straighter, and it looks like it's approaching a rectangle, or at least a parallelogram. That is, what happens if I take infinitely many of these? That's the idea that the ancients had. And when you take infinitely many, then it becomes that shape. I can't draw infinitely many pie slices, but hopefully you can believe that in the limit, that's what this column was called, take it to the limit. Yeah. Anyway, it is a nice, we are taking it to the limit of infinitely many pie slices. We get a rectangle, and everyone knows the area of a rectangle. It's that times that. So pi r times r, that's pi r squared. That's really the truth of why the circle has area pi r squared. So, did you get a little chipper? Good. Okay, good. If you're, a pro, you've seen other arguments. Maybe you don't like this argument, but it's a pretty nice argument. It really exposes exactly what's going on, and that infinity is crucial in this. You can't calculate the area of a circle without resorting to infinity in some way, because it's round. You can calculate areas of things with straight sides, but round things require infinity. That's part of what calculus is about. So in that, I feel like people who never took calculus can get a feeling of how intimately infinity is connected with it. Well, okay, I think I want to just show 1 or 2 more examples of how to try to communicate. And so the next one is one that has graced the poster that you may have seen around campus with bathtubs on it. People were asking, what's that bathtub? And this is, oh, I'm not going to do that. That's a nice proof, too. Well, let's not do that. Here's a bathtub. Now, my Uncle Irving, my father's brother, was his partner in the shoe store that they owned in our little town. And he worked upstairs in the office, whereas my dad would talk to the customers and try on shoes with them and nice to them. Uncle Irving, difficult sort of guy, not so good with the customers. So they kept him up in the office. Anyway, Uncle Irving would ask me a puzzle every time he saw me, with a nasal voice. I'm not going to imitate him, but so he asked me this puzzle one time when I was maybe 10 or 11. Suppose you have a bathtub and water is pouring into it from the hot water faucet and the cold water faucet. And if notice that it looks like it's really pouring out fast from the cold water. It's kind of dripping out of the hot water. He says if the hot water would fill up the whole tub in a half hour, but the cold water would take an hour running by itself. How long would it take when they're both running at the same time to fill the tub? You get the question? One would take 30 minutes to fill the tub. The other would take an hour to fill the tub. How long when they run together? So I said 45 minutes. Okay, now you should laugh at that, because that's a foolish answer. we know that one of them running by itself would only take 30 minutes. It can only be helped by the other one. So it cannot take longer than 30 minutes. And so Uncle Irving thought this was funny too, and he laughed. Because I was 10. And, he said, no, Stephen, very foolish answer. And so then he schooled me. He said, here's how you should think about it. You should think, okay, in 1 minute, how much would be filled up by the fast one, the cold water? In 1 minute, it would fill 1/30th of the tub. As I said, it would fill up a whole tub in 30 minutes, in a half hour. So in 1 minute, it would fill up 1/30th. The other one would fill up 1/60th. So running together, they will fill up 1/30th plus 1/60th. So now we have to do common denominators, and it'll end up being 2/60th plus 1/60th. It'll be 3/60th. That's 1/20th. It'll take 20 minutes to fill the whole tub. Okay, so that's Uncle Irving's answer, 20 minutes. Correct. Okay, so that I don't think is an elegant calculation. It's a correct calculation, but that question stuck in my craw for many years, partly because of the humiliation. I was embarrassed that I gave a really stupid answer, and Uncle Irving laughed at me. So I thought about the question for many years. What's a better, okay, his fraction thing is good, it works, but my point in this example is to get you to think creatively, that math is not, you often hear people say, what I do or don't like about math is that there's only one right answer. Right? Some people like that. Some people say that's what's great about math, that there's a true answer and there's only one right answer. Other people don't like that. They think it's very authoritarian and rigid and unpleasant that it's like that. They want more freedom. So it's naive. Yes, there's one right answer, but there are many routes to the right answer, many ways to be creative. So let's think about this. For example, one thing we could do is to be approximate. Rather than trying to get an exact answer, we could get information a la Sherlock Holmes. Like we could say, we already know, if just one faucet were running on its own, it would take 30 minutes. The fast one. So we know the answer is less than 30 minutes. That's some information right there. Another thing we could say is, why is the problem so confusing? It's confusing because they're running at different speeds. What if they both ran at the same speed? Would that give us information? Like suppose they both ran at the speed of, I don't know. How about they both ran at the speed of the fast one? The thing that can fill it up in 30 minutes. If they were both running at a speed that could fill up the tub in 30 minutes, can you see obviously how long it would take? Yes, you can. Don't worry, I won't laugh or humiliate you. Go ahead, what would you say? How long would it take? Yeah, you nodded like 15 minutes, correct. You're right. Beautiful. Is that what you other people were thinking? Right, because if they're running at the same speed, it's like you take the left side of the tub, I'll take the right side, and we'll both do our thing, and we'll fill up half the tub. And yes, 15 minutes. That's right. So, but now what does that tell us about the problem we were supposed to do? We were supposed to do one that was fast and one that was slow. We just did your problem that was fast plus fast. And so fast plus fast only took 15 minutes. So we know the real problem has to take a little longer than that, because it's not fast plus fast, it's fast plus slow. Right, so now we know the answer, whatever it is longer than 15 and less than 30. When we did no math, see, there are no common denominators. This was just thinking. Still with me? Yeah, so it's somewhere between 15 and 30. Now, how can we get the answer without doing common denominators? And here's how. This is what's on the poster. As I thought about it as the years went by, I thought what's really unpleasant or tricky about the problem is, again, these different speeds. So and also it's confusing. The hot is getting in with the cold, and they're mixing up, and it's hard to keep track. Really, it's like this, you have to identify what's the problem. So I'm going to not let them mix. I'm going to imagine a surreal, some bizarre painting of bathtubs on conveyor belts. And they're just going, there's a cold water faucet and there's bathtubs streaming by, getting filled up. And then there's also the hot water faucet, bathtubs streaming by, getting filled up. Now, let's watch what would happen if you watched for 1 hour, how many total bathtubs would be filled up? 3. Why did you say 3? Because one of them would fill 1 bathtub in an hour, and the other would fill 2 bathtubs in an hour. 3 bathtubs in 1 hour is 1 bathtub in 20 minutes. So I think that's an elegant argument, and it requires this surreal thinking. But that's fun. That's part of the fun of math, is to just be imaginative. So okay, that's in this new book, Joy of X, the whole thing with your Uncle Irving story, and it's about word problems, which kids who are in high school algebra and their parents think, why are you taking these horrible, you know, like there was that vicious essay in the paper the other day. Is algebra necessary? You know, how stupid algebra is. And like, yes, this is a terribly contrived problem. Nobody has a bathtub, you know, with a faucet like that. We know that. We know that. Yet, I claim that just like listening to a really sweet piece of music or beautiful poem or surreal paintings, there's something beautiful in this problem. If you chill out and savor its beauty and think about it, let it wash over you. They take years. I mean, this took me years to appreciate this problem. So word problems can help you think. No one cares about bathtubs. If you're a plumber, maybe, but this word problems are to help you think and also to help you tease out what's confusing from what's simple and so on. Anyway, there's value in word problems. So my last example, I guess, will be a case where I think I went off the rails, maybe. Because what did I learn from doing this series about communicating? And I think I might have learned one thing, but I'm not sure if this is true, but I'm going to throw it out there for you to entertain as a conjecture, which is I had one article that, let me find it for you. Pretty early in the series. So here it is. It's you're about halfway through. It's called Think Globally. Right? Act locally, think globally. It's about a subject that mathematicians would call differential geometry. And most people haven't studied it, but it's really a pretty subject, and I wanted to give a flavor of it. And so the first thought was, let's talk about flying to Rome from New York. Before I get into the example, maybe I should say one person had suggested to me, Carl Zimmer, who writes about biology frequently for the Times, said that online is different from in a newspaper. That not print. When you're online, you can use color easily. That's nice. But you can also show videos, like I did with Sesame Street. The medium is much more flexible. And so he said one approach to writing your blog could be think about some really cool video you want to show and build the article around that. Do whatever it takes to get to that. So that's what happened with this piece. There was a video that one of my colleagues showed me, which I'll show you at the end, that I thought was cool, and I'm going to build the whole thing around this. So I'll get to that video, and it was a total dud. I hated this, including my wife.